some applications of multiplexers. So that's what was in our previous class. That was a quick introduction of what is going to follow in this unit. Sorry. So, I mean, this all is to be covered here. Now, we had seen this multiplexer. What is a multiplexer? Means the multiplexer circuit helps us to choose one of the multiple inputs available. Now, this already has been discussed, so I won't be talking. This is the circuit of a multiplexer. This was another way of implementing a multiplexer. This is a general block diagram for a multiplexer, n is to 1. We talked about what is the role of this enable input. So this is active low multiplexer, means whenever this G is low, this multiplexer will be active, and so on. So this was discussed. All right, so now let us, I think this also was done, that how we can try to see the internal circuit diagram for a 16 is to 1 multiplexer. Means here we have 16 different inputs, and this multiplexer based upon what is the select bit values. So these are your select bits, A, B, C, D, right? So depending upon what is the value of these select bits, any one of the 16 inputs will be passed on to the output. How it is done, you can see the circuit little carefully and try to see that suppose ABCD is like, okay, 1 0 0 0. Okay, let us take the simple example. ABCD is equal to 1 0 0 0. You look at this circuit and let me know which particular input will be fed to the output Y. Y is equal to which one of these inputs? When ABCD is 1 0 0 0. Okay, just a quick rough work. Do it quickly and let me know. Can you see the circuit clearly? It will be D8. How? You can check. When A is 1, then you can see that when A is 1, then you can see here is the connection, and this goes to D8. Okay? Other all are zeros. So they are not gates. You will realize that at D8, A connects directly. At D8, A connects directly, whereas B, C, and D, their complements connect at D8. You can check. At D8, this is B complement connected. Each dot here represents a connection. Okay. Similarly, here is C complement. You can see. I hope you can follow the cursor. Similarly, this is D complement. So when this is 1 0 0 0, D8 will be selected. So accordingly, you can check for different combinations of ABCD. Any one of the inputs will be fed to Y. Okay. Now, next thing which we want to talk is applications of multiplexers. How we can use multiplexers to design digital circuits. Suppose you have been given any truth table. Earlier we saw that how, with the help of simplification of K-maps, we can realize any truth table or any circuits in terms of a minimum number of components. Okay. Now here we will see that how a multiplexer can be used to design any truth table. If you have been given any truth table, how can you use multiplexer to actually design the expression or the function, digital function, implemented or required to be implemented in a truth table. So first thing is that, I mean, why this is or why usage of multiplexers is very important is that if we are using multiplexers, we don't need to simplify the circuits. Don't need to simplify. Like we don't need to go to even K maps and do all that simplification. These multiplexers give you straightforward way of implementing the uh, any truth table. So we will be seeing this in the example now, which is going to follow. Second advantage is that it minimizes the IC package count. I mean, okay, what you need is only one single IC for a particular truth table to be implemented. We will see that also how it is possible. And this offers a very simplified logic designs. How this is done, let us see this with the help of the following example, which is going to come up. But before that, what we need is actually, if we want to use a multiplexer for implementing any logic circuit or a logic element, then we need actually canonical form for that particular expression. That is desired. Because of that, we can simplify things a little, a lot more. You can see, I mean, let us see this. What is the process? What is the procedure for implementing any truth table? First thing is you need to identify the decimal number corresponding to each min term and max term expression. We will have already a canonical form. Suppose we have a canonical form. Okay. Either it will be in terms of min term or it will be in terms of max term, right? So what actually, let us see, we want to use min terms. So what we will be doing actually in first step is to identify the decimal number corresponding to each min term in the expression. Once it is done, the input lines corresponding to those numbers are connected to logic 1. So what we shall be doing is, we shall be connecting the input lines to those numbers to logic 1. Okay, then what you will do is, all other input lines will be connected to 0. And that's it. The input lines are to be applied to the select inputs. Because if you have any truth table, what is a truth table is made up of some inputs and outputs, right? Some inputs, and corresponding to that, what should be the output. So those inputs actually has to go to the address bits or select inputs. Let us see one example first. Okay. Now let us see that how we can implement actually this truth table. This suppose has come from a truth table. Now I'm sure you know how to get this form into truth table form, right? So what this means, it is a expression in terms of min term. It is a sum of product or SOP. It is helpful to write down SOP or POS. Okay, I would request you quickly write down whatever expression, either SOP or POS promise. State which one will follow directly, straightforward. It is in term of min terms, right? Small m means min terms, summation over this. So this would be sum of products, right? M naught plus M2 plus M3 plus M6 plus M8 plus M9 plus M12 plus M14. So there will be a corresponding sum of products, right? So M naught would mean what? M naught means what? Okay, let us say A, B, C, D are inputs. What is M naught equal to? Yes. M naught is A bar, right, correct? Similarly, what is M2? M2, M3, let's write down all the terms. M2 is A bar, B bar, C, D, 0, 1, 2. M2 is what? A bar, B bar, C, D bar. Yeah, correct. Similarly, M3, M6 and so on. Well, very good. So once you follow all these terms, you can actually find out the truth table as well. And what will be the truth table for this? Okay, let me give you a quick homework. Just right now do it, not for later on. What will be the truth table for this? You design A, B, C, D, write down various combinations, that is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, then 0, 0, 1, 1, 0, 1, 0, 0, and so on. And what will be the output Y corresponding to this? Before I proceed further, I request you to write down the truth table. Quickly write down truth table in your notebook. Once done, just let me know. I'm waiting for your response. Once your truth table is completed, type a message. Yes, anyone completed truth table? I hope you are working on truth table. It's not that lengthy thing. Is it done? Pallavi, is it done? Okay, Divanshi says done. Done, done, done. Very good. Now, if you have truth table with you, then let us see this implementation. Now, this is a 16:1 multiplexer. Since we had 4 inputs, so we need a 16:1 multiplexer. And what we will do, for this case, we will connect. So you will be having 16:1 means you will have 16 inputs. 0, 1, 2, 3, 4, 5, 6, isn't it? You will be having 16 inputs. So what we do is we connect 0, I mean 0th input, then 2 sitting in the midterm, second input here, 3 also connecting this, then is 6 here, so 6th input will also be connected to logic 1. All these inputs which are appearing in sum of products form, canonical form rather, those will be connected to logic 1 and remainings are connected to logic 0. So now what will be the operation of this circuit? Now let us try to compare our truth table with what this multiplexer will give. So in case 0, 0, 0, 0, what will happen? 0, 0, 0, 0. This multiplexer will select which input? 0th input, isn't it? And what is that? It is at logic 1. And that input matches with your truth table, right? When all A, B, C, D are 0, output is 1. Correct? Let's take another thing. When 0, 0, 0, 1, when this is 0, 0, 0, 1, what will happen? This logical input will be selected, isn't it? So what is that? 0. And that also matches with your truth table. Correct? Similarly, you check all of these and then uh, let me know if whole truth table comes up correctly or not. Quickly check it so that I can uh, I can be assured that you all got this implementation of any truth table using multiplexer. Is everything fine? Is every entry of the truth table matching when we employ this circuit? So this is active low. So we already have connected this to ground, means this is the circuit is active. That's fine. Yes, quickly let me know. Check it, take your time, give you 2-3 minutes. You take your time and then check the truth table thoroughly and see if it is implemented correctly with this multiplexer circuit or not. Okay, well, then we got it correctly. Let us see some more responses. Others as well, are you able to get the matching with the truth table? Okay, well, we got it. Very good. So now, I hope you are in a position to understand that how we can use multiplexers to implement any logic element or any truth table. Okay? So accordingly, you have to choose how many number of inputs are there, and then we have to choose corresponding multiplexer and then fix the output. Correct? I mean, fix the inputs at logic 1s and logic 0s according to what is the requirement. You have to first actually follow this one, uh, canonical form of sum of products. Okay, other question. Can we try the same using product of sums? I mean, suppose you have been given a product of sums expression. Can we use a multiplexer to design that circuit? Yes. In that case, what will happen? All the terms sitting here in product of sums form shall be connected to the logic 0 and others to logic 1, and that's it. Okay. Same thing. I mean, if this thing, if you follow the complementary theorem, what will be the product of some expression for this? Pi, capital M, 1, 2 is already here, so 2 won't be there. 3 is also not going to be there. 4, 5, so pi, 1, 4, 5, and so on. Others, inputs other than this. Right, that will be the product of sums. So what we shall do, we shall connect all product of sums terms, that is max terms, to logic 0. This is logic 0, correct? And others to logic 1. That is also equivalent way of stating the same thing. Is this clear? Is this clear or any question till now? Okay. Meanwhile, also sign your attendance. Subhash. Subhash is present? Yeah, very good. So, well, let us see next thing. Now, suppose you have been given this truth table. Suppose you have been given this truth table. Can you try to implement this using multiplexer? And just to let me know that what size of the multiplexer is required to implement this circuit or this truth table. This is again a homework, that what is the size? Size means, is it to be 2 is to 1, 4 is to 1, 8 is to 1, 16 is to 1? What kind of multiplexer that should be? So this is the truth table. 16 is to 1. That's correct answer. Very good. No, it's not a 15 is to 1, Tanvi. The total inputs are 16. It begins from 0, right? So 0 to 15 means 16 because 0 is also sitting. Na? So it is 16 is to 1. That is fine. Correct. Almost everyone answered it correctly. Now, question is, how can you implement this truth table using that 16 is to 1 multiplexer? First, you do it quickly, and then let me know your circuit diagram, what you got. I would like to see quickly in your notebook with the help of your live camera. First, draw the circuit diagram, and then let me know if when you get it. Okay, that will be a quick practice. Okay, you try it. Giving you how much? 5 minutes maximum. Okay, I'm giving you 5 minutes for this. You get it done. Then once done, you type here the message and then place your notebook in front of your camera so that I can see what is the outcome. Yes, please. Yes, is it done? Anyone? Yes. Anyone could do this? Okay, someone is showing up the camera. Very good, Tanvi. Unfortunately, I can't see it clearly, but okay. Okay, I leave it to you. I mean, you upload it. I will create an assignment. You upload this in your assignment work. Okay. Well, so now there is another question. Can we really get this same circuit from lesser demultiplexer, lesser multiplexer? I mean, instead of using 16 is to 1, is it possible to do the same job done with the help of 8 is to 1 multiplexer? So now is the answer is lying here. Means, suppose you don't have a 16 is to 1 multiplexer, only you have a 8 is to 1 multiplexer, but you have to implement this circuit. So that can also be done. How? Now let us see with the help of this another table. So this table is nothing but the same truth table, but now we are representing here not 0 or 1, but something in terms of D. Now you see, first one. So whenever A, B, C are 0, doesn't matter whatever is D, output is 0. So we have written clear cut 0 here. Okay. Now second thing, whenever A, B, C is 0, 0, 1, so all both these rows correspond to A, B, C being 0, 0, 1. What is the output? Output is when D is 0, Y is 1. When D is 1, Y is 0. So it is D complement, isn't it? Now, second thing, this one again when 0, 1, 0, output is again D complement. You can check. Okay. Now, second thing is okay. Next thing is what if it is 0, 1, 1? You can see this is 1. So now, irrespective of whatever is D, output is 1 always. Correct? So that is why we have said output is 1 and so on. So now you can check that this truth table contains only 3 inputs. D is also input, but it is now going in such form that it is appearing in truth table in this form. Now question is how this helps in implementing this same expression using a 8 is to 1 multiplexer. So you can see this is the circuit. This is a 8 is to 1 multiplexer, and there is a logic 0. Of course, you will have both 0 and 1 with you. There is a logic 1 as well. Now you can see from here that 0 in terms of min terms, and this is 1, 2, 3. So 0, 3, and sorry, not 3, I mean 0 only. 0th input will be at logic 0. Correct? And 3 and 5 will be at logic 1. You can check here now. 3 and 5 are at logic 1. Okay? And what about others? Now, for others, we have two options. D directly, this is D going directly, and D bar. So now you need just a NOT gate, additional NOT gate, and that's it, isn't it? So what will that do? All those places where D complement is there, so those are connected to D complement. So that is going to be 1, 2, and 3, 4, 5, 6. 1, 2, and 6. So 1, 2, and 6 are connected to D complement. You can check, right? And remaining, which one? 1, 2, 3, 4, 5, and 7 are connected to D. So you can check, isn't it 5 or 4? This is 4 and 7. Let us check. 0, 1, 2, 3, 4. Yeah, 4 and 7 are connected to D directly. So is it clear that, I mean, how by using 8:1 multiplexer, even we can use the expression for 4 input truth table. We don't necessarily use need a 16:1 multiplexer. Even 8:1 is capable of doing that. But there, of course, we have to do some homework, and this table is the additional homework. Is it clear, or any question from this part? So now, can you implement, there is another question now. Can you implement any 4 input truth table with the help of 8:1 multiplexer? Is that general, or it was specific to this truth table? What do you think? Is it general, or it is specific to this truth table? Yes? Am I audible? You can try it for any truth table. Okay. Before we proceed further, okay, I give you a homework to you now. You have to use the truth table. You have already have this truth table with you, right? So you have to use the truth table of this and implement that using 8:1 multiplexer. Okay, that's the homework now. Means you follow this truth table and implement the same using 8:1 multiplexer. We have seen 16:1 multiplexer for this. Now you have to do it with the help of 8:1 multiplexer. Okay, now let us proceed further and try to understand what is this multiplexer tree. So what we have seen is that highest multiplexer which we have is, in terms of ICs, is 32:1, 16:1, I think, available to us. I'm sorry, I didn't put those tables which gives the IC numbers which corresponds to different truth tables. Let me quickly show you that also. Just give me a moment. I will put those tables in the presentation and then share the numbers, IC numbers with you. Just give me a moment. Huh? Okay, so here follows the table which summarizes the IC numbers. Yeah, here is the IC numbers which are available in the market in the form of multiplexers. You don't have to, once you have to get a multiplexer, then you don't have to actually go to AND gate and OR gate and design your own multiplexer with the help of those basic gates. But there are available ICs in the market which has different multiplexers implemented. So this 74157 is a I mean, it contains 4 2:1 multiplexers. Okay, what it has is, it has 4 2:1 multiplexers integrated into same IC. This one has 4 2:1 multiplexer, again, same thing, but the difference is that this multiplexer gives same input, same value as the input, This gives you complement of the input. Okay, both ICs are same 7 8. Only difference is 7 gives Y equal to data bit value, and in this case Y is equal to complement of the data bit. So depending upon the requirement, you may have to use any one. So this contains two 4:1 multiplexer. This IC 74153 contains 4, dual means 4, sorry, two 4:1 multiplexers. Okay. Similarly, this one has same thing, inverted, and this is same as input. This gives you inverted input. This is the IC number for 8:1 multiplexer. Same thing, complementary outputs. This is also 8:1 multiplexer, inverted input. Complementary output, I don't know. I mean, it should be same as the input. I will check it. I mean, what is the meaning of this? This should be same as the input, I think, because this is inverted input. That's fine. Similarly, this is 16:1 multiplexer, 74150. Means it is a 16:1 multiplexer. So this IC will be having 16 pins for input, then 1 pin for output, then some bias voltages, some active pin. Active pin means say that G1. I mean this one, ground pin. This is not ground pin, but this is the pin used to activate particular multiplexer. So all those kind. So I leave it as a homework to you. You do it yourself on Google. Try to find out how many pins are there in these ICs, and what is the pin diagram of each IC. I mean, how to identify which pin corresponds to what. Because IC has certain pins, right? So you have to identify which pin is for what purpose. There has to be, for example, in 16:1 multiplexer, there has to be 16 pins for inputs. So you should be in a position to identify in this IC which particular pins are for inputs, then which is for output, and so on. So this is as a homework left to you. Let's move further. That's about multiplexers. Now let's see. Now suppose we need a 32:1 multiplexer. So highest IC available in the market with the corresponding to a multiplexer is 16:1 multiplexer. Now question is how we can get a 32:1 multiplexer by using two 16:1 multiplexers. So this is the circuit. Now let us try to understand this circuit first. So this is one 16:1 multiplexer. This is another 16:1 multiplexer. So this, since this is 16:1 multiplexer, so it should have what? 4 inputs, correct? So these are 4 input, rather we can say the address bits. So what we do is all these 4 inputs are connected to each other. Now try to see. These are two 16:1 multiplexer. There all the inputs are connected to each other. And what are they named? So this is least significant bit indeed, actually. Correct? So this is called E, and we call this as least significant bit for a 32:1 multiplexer. So for a 32:1 multiplexer, there has to be 5 address lines. 5 address lines means 1, 2, 3, 4. There has to be one more, 5th. That is why 2⁵5 would lead you 32 input options, right? So now you have 32 inputs, 16 for one, 16 for second, correct? So we name them like 0, 1, 2, 3, 4, 15, 16, all the way up to 31. Now how does this circuit work? Try to see something really interesting. So these active low or activating pins, these pins are used to activate the IC, correct? And then we connect their output of these two multiplexers to a OR gate, and the same is fed to the output. So this is the output for 32:1 multiplexer. How this works now? What we did is we connected this and this with the help of NOT gate to these two ICs. Now this is the most significant bit for that 5-bit input system. because 32 is to 1 multiplexer has to have 5 inputs. So these pins are used for that purpose. Now, how does this circuit work? I don't know if it is clear. Are you getting me properly, or is there any question or confusion? Are you getting what I'm trying to talk? This 32 is to 1 multiplexer, what is it? And how the connections are made? Okay, very good. Now let us try to see the operation. Now try to draw a truth table with 5 inputs. A, which is most significant bit, then B, C, D, and E, which is least significant bit. So when A is 0, B 0, C 0, D 0, and E also 0. So what will be selected to the output? Now since A is 0, and this is an active low multiplexer, means whenever G2 is low, then this multiplexer will be selected. Otherwise, it won't be. Okay. Now, since A is 0, NOT gate is here, so this will be 1. So this multiplexer IC is off, out of the way. Now, this is 0, so this IC is on, or it is activated. Output is output of this IC or this IC, so that's okay. So 0, every other bit is also 0, 0, 0, 0, 0, 0, right? All 5 are 0. So what will be selected? Now this IC is activated, and B, C, D, E all are 0. So what will be selected is this bit. This bit comes here to Y1, and output will be nothing but Y1. Correct? When you change, so this will, first 16 outputs will be following from this, as long as this remains 0. As long as this remains 0, this multiplexer is selected and it works routine way, as a 16:1 multiplexer. Now when you go to A is equal to 1, then all may be 0. What happens? Immediately you switch into this IC. So this is for 16th input. Suppose here you have applied 16th input of this multiplexer. So then this will select 16th when this is 1, and B, C, D, E all are 0. Then this will be D16, and then D16 will be equal to Y2, and that will be nothing but F. So that is how a multiplexer tree can be used to actually increase the size of a multiplexer. How we can use two 16:1 multiplexers to get a 132:1 multiplexer. Is this clear, or any question? Okay, very good. If it is clear, I think it is Subhash, what you're trying to say? I didn't get your question. What you're saying, Subhash? I didn't understand. What is this spelling? Specify, yes. Subhash, what you want? Are you having a question or what? Oh, you do so many mistakes during the class. Okay, anyway. So everything clear? Fine. Now, somebody may ask, you may say that, okay, I don't have even a OR gate. Means suppose I have to get 32:1 bit multiplexer from 16:1 multiplexer by using only multiplexers. So well, then what you can do, instead of using a OR gate, we can use a 2:1 multiplexer. So here is one 16:1 multiplexer, another 16:1 multiplexer. These are connected to logic 0. Both are activated, means, okay. These are your B, C, D, E, the E being least significant bit, the usual way. And this, because if you have a 2:1 multiplexer, means there is a data bit, address bit for that, isn't it? So for 2:1 multiplexer, the select bit is only 1. So this is one select bit which will be most significant bit. So what will that do? When this is 0, it will select all the inputs. I mean, it will select the output of first multiplexer. And whatever is happening here is useless. When you take A is equal to 1, then this multiplexer input is selected to the output. So that is how we can get 32:1 multiplexer by using only multiplexers, not even a OR gate. Is this circuit clear or any question on this? Is this okay? Oh, well, very good. So, sorry, this is fine. Then that completes our topic of multiplexers. Means uh, by now we saw what is a multiplexer, how a multiplexer can be used to design any truth table, how we can combine more than one multiplexers by the means of what we call the multiplexer tree, how we can get the job done with the help of a smaller size multiplexer, isn't it? We had 4 input truth table, but then we got the things done using a 3:1, I mean, sorry, 8:1 multiplexer. So having done this, now let us move to the next topic, which is demultiplexer. So as the name indicate, what is a demultiplexer? It is opposite of a multiplexer. So what does multiplexer do? A multiplexer have n inputs and then one output. So based upon what are the address bits, based upon what are the address bits or select inputs, output is equal to any one of the inputs, isn't it? That's what is a multiplexer. Demultiplexer is opposite of it. So you have a single input. Now depending upon what is your select inputs, that single input is provided at any one of the outputs. So when select bits are 0, 0, 0, 0, whatever is here at input will be available at D0. When it is 0, 0, 0, 1, whatever is at input data is available at D1 and so on. So that is what is called a demultiplexer. Is this clear? Demultiplexer? Now question may be ki how to get this demultiplexer operation done. This is the simplest example of it. 1:2 demultiplexer. You have one input which you call the data input, and then you have one select input A. So what is at Y naught is decided by what is the value of A. So if A is 0, Y naught is equal to D. Or when A is 1, Y1 will be D. So this D is selected at Y naught or is provided at Y naught or Y1 based upon what is your A. Is it clear? 2:1 demultiplexer clear? Now here is a 16:1. Sorry, 1:16 demultiplexer. Demultiplexer is also called decoder. We will be talking about this in the next lecture. What is a decoder? But this is a 1:16 demultiplexer, 4 inputs. Now you can check based upon what is address bit ABCD. This data bit is provided or supplied to any one of the outputs. Can you see this, how it works? Now you can see in this circuit that when A, B, C, D all are 0, so this AND gate, every other input of this AND gate is connected to A complement, B complement, C complement, D complement. So when A, B, C, D all are 0, so all these inputs of this AND gate are 1. Now its output is decided by what is D. So if D is 0, Y naught will be 0. If D is 1, Y naught will be 1. So we can say Y naught is equal to D, the data bit. And when you have 0, 0, 0, 1, A0, B0, C0, D1. So now D1 means you can see here, this gate connects to D directly. And other inputs of these gates are connected to A complement, B complement, C complement. So in that case, Y1 will be D if A, B, C, D are 0, 0, 0, 1. So that is the simple operation of a demultiplexer. Is this clear? Or any question from this part? Demultiplexer. What is demultiplexer? Is this okay? Well, so if this is clear, that's all for today. Tomorrow we will be seeing some applications of these demultiplexer or circuits based upon demultiplexer. Well, that's all for today. Any question from overall lecture of today? Any question?